In this video, we're going to go over the second half of Chapter 7. We've got a few new terms that we're going to cover, so actually all of these that are left we're going to go over. We talked about iso-quant, marginal rate of technical substitution, and iso-cost line in the first half of Chapter 7, and we're going to talk about these terms that are left in this half. Before we get into it, let's review a couple cost vocabulary terms. So if you recall, variable cost, fixed cost, total cost, and average total cost. Variable costs are the costs that change or vary as the level of input use or quantity of product produced changes. So for example, if we're talking about a crop farm and we go from producing 30 bushels to 6,000 bushels, there will be costs that will change because we are producing more. We're going to have a change or an increase in seed, fertilizer, pesticide, labor, and fuel costs. So anything that increases or decreases as production increases or decreases, that is a variable cost. If we're looking at a cookie factory, the cost associated with sugar, flour, chocolate chips, butter, and eggs, all of the ingredients, would increase or decrease if we increase or decrease the amount of cookies that we're making. Fixed costs, on the other hand, do not change if we're increasing or decreasing our level of production. So whether we are producing, whether we're farming, let's say, 100 acres or 200 acres, we will still have the same combine costs, the same planter costs, the same storage shed costs. So those are fixed costs that do not change when we increase or decrease our production. With the cookie factory example, whether we are making 500 cookies or 1,000 cookies, we will pay the same in kitchen rent. We'll pay the same for our electric mixers, our bowls, our food handlers licensing fee, and our insurance fee. So it doesn't matter, again, if we're making 500 or 1,000 or 1,000 or 2,000 cookies, the price that remain the same across the board are fixed costs. And then total costs are the combination of variable costs and fixed costs. So we add those together to get the total cost. And then average total cost is how much money that it costs to make one unit of product. So if we're talking about a crop farm, we would figure out how much does it cost to make one bushel of corn. If we're talking about a cookie factory, how much does it cost to make one cookie? Let's look at a quick example that helps us solidify our understanding of variable costs and fixed costs. So if Grace makes 500 cookies per month, what is her average total cost to produce each cookie? If Grace makes 3,000 cookies per month, what is her average total cost to produce each cookie, given these costs? So if Grace makes 500 cookies per month, her average total cost, so again, total cost is variable cost plus fixed cost. So let's first figure out what her variable cost per cookie is. So her variable cost per cookie, flour costs 2 cents, sugar costs 3 cents, eggs cost 5 cents, butter 7 cents, and chocolate chips 8 cents. If we add all those together, 2 plus 3 plus 5, that's 10 cents. 7 plus 8 is 15 cents, 15 plus 10. So if we add all that together, this is 25 cents per cookie. Okay, and if she's making 500 cookies, we're going to take that 25 cents times 500. And that is going to equal 25 cents times 500 is $125. So in variable costs to make 500 cookies, it's going to cost her $125. In fixed costs, she has kitchen rent that costs $100 per month. She has an electric mixer that costs her $30, a food handler license that costs her $50, and insurance that she has to pay that costs $20. So her total fixed costs are 100 plus 30 plus 50 plus 20. So that is $200 total if we add all that together. So her total costs are variable costs, $125, plus her fixed costs, which equals $325 to make 500 cookies. but we're being asked what is the total cost to produce each cookie. So we're going to take that $325 and we're going to divide it by 500. 325 divided by 100 is 65 cents. So it's costing her 65 cents per cookie when she produces 500 cookies. Okay. Now, if she increases production to 3,000 cookies, let's see what that will cost. If she increases production to 3,000 cookies, this still adds up. Her variable cost per cookie is still 25 cents. Okay, but now she is producing 3,000 cookies. So that variable cost changes because she's increasing her production. So now instead of $125 in variable costs, 25 cents times 3,000 is $750. So variable costs now are $750. Her fixed costs are going to remain the same. She is using the same kitchen, the same electric mixer. She still just needs one license and she just needs one insurance coverage. So her fixed costs are going to stay the same at $200. So her total costs are $750 plus $200, which equals $950. And that's the total cost for 3,000 cookies. However, we want to know what is the average total cost per cookie. So we're going to take that $950, divide it by 3,000, and we are going to get approximately 31 cents per cookie. So we did this exercise to show you that as you increase production, your cost per cookie, or your average total cost, tends to decrease, at least at first. So we went from it costing us 65 cents a cookie to 31 cents a cookie. And that is because our fixed costs stayed the same at $200, and this $200 now is spread over a larger number of cookies, which allows the price per cookie to decrease. Okay? Okay, now we're going to differentiate fixed and variable costs as they relate to the short run and the long run. So the short run just means in a short period of time. The long run refers to a long period of time over many, many years. So in the short run, some costs increase or decrease with an increase or decrease in production, and they are considered, those are our variable costs. Okay, if they increase or decrease as we increase or decrease production, those are variable costs. While costs that remain the same with an increase or decrease in production are considered fixed, right? So that was the previous example, the electric mixer, the kitchen rent, etc. So for example, in a cookie shop, flour, sugar, eggs are considered variable, while building, rent, licensing, insurance are considered fixed. I'll review. This is the new information though. In the long run, so over many years as a business potentially expands, all costs are considered variable. This is because over time a business can expand its production to a point where they may need to purchase more capital equipment. So a building that was rented in the short run for a cookie shop was, at first, we considered that a fixed cost, the building that we rent. But if we start to create so many cookies that we need to have additional kitchen space, we need to have additional electric mixers, we need to have multiple people with food safety sanitation licenses, we need to hold a higher level of insurance. All of these things that were once fixed costs now become variable costs. So a fixed cost is only fixed for a particular levels of production. Once we get so large, we need to increase that capital equipment expenses and the insurance and so on and so forth. So in the long run, all costs are variable. we can plot short run and long run average cost curves. So the short run average cost curves for a particular business are these little U-shaped curves in here. Okay, the long run average cost curve envelopes all of the short run average cost curves underneath. And what these cost curves are telling us is the output is on the bottom, so it's telling us basically at 400 units of output, 400 units of output are going to cost an average of $30 per unit. 800 units of output are going to cost an average of, oh, that's also 30. 1,000 units of output is going to cost an average of $40. So the long run average cost curve envelopes all the short run cost curves, and it envelopes them at their lowest costs of production. So the lowest point of production for number one here is right here at about 47, and that's where the long run average cost curve meets the short run average cost curve for that first firm. So we have all of the lowest points of each of these, and then the long run average cost curve envelopes all of those. When we plot the short run and the long run planning curves, this helps companies figure out what size they should operate. Should they get bigger and produce more, or should they get smaller and produce less? It does this by helping them figure out what is their lowest average cost at particular outputs. Okay, so these curves indicate the minimum product price at which any output can be produced in the long run. So you can refer to this article to answer some of these questions, but I'm going to go over most of them here too. Okay, so when we're reading this graph, first question, what does SAC1 stand for? That just stands for short run average cost curve. Okay. B, scaling up means that a firm gets larger and is going to make more product. Which firm is the largest, making the most product? Well, all we have to do is we have to look at the output along the bottom. So we go from output to 200 to 400 to 600 to 800 to 1,000 to 1,200. The one that is making the most product is is firm number 5. Okay, so I probably should have just put number 5 there. Okay, so these SAC1 is going to produce at lower outputs. SAC2, we're getting a little bit bigger, and so on and so forth. So we continue to scale up as we go across the long run average cost curve. So what does LAC stand for? That stands for long run average cost curve. Why does the short run average total cost curve at first fall with increased output? This has to do with the economies of scale, or it has to do with the example that we looked at with the cookies, Grace and her cookies. So the fixed costs are basically getting spread over a larger number of output. So our average total cost will fall. So we could just say fixed cost is remaining the same as production increases. As production increases, so average total cost decreases per unit. Okay, so that goes back to that cookie example with Grace's cookies. Letter E, what does the lowest point on each of the short-term average cost curves represent? So here is one short-term average cost curve. Here's another, here's another, here's another, here's another. So the lowest point represents the most efficient level of production. In which that firm is utilizing all of its fixed costs to completion. So the article talks a little bit more about this, but basically the firm is fully utilizing the scale of operation. So if we're talking about the cookie factory, we've used up all of the tables in that space. We've used up all of the electric mixers. We've used up all of the insurance and so on and so forth. And so it's the most efficient level of production. If we start making more cookies, we get less efficient. Okay, and that's why the cost curves start to increase. Letter F, if a plant needs to make 800 units of product, what is the lowest average total cost they can make each unit for? Okay, so we need to imagine that these cost curves actually continue to go out. Okay. So let's see, did I get all of them? Yeah. All right, so at 800 units then, if we follow this up, it's going to cost firm 4 $30 to make 800. It would cost firm 3, $35. It would cost firm 2 $50 to make 800 units, and it would cost firm 1 $70 or $80. So if a plant needs to make 800 units of product, what is the lowest average total cost they can make each unit for? That would be $30, and they would have to operate at the scale that firm 4 is operating at. Okay, G says identify which areas of the scrap represent constant return to size, increasing return to size, and decreasing return to size. We're going to skip that one because we're going to hit it in the video we're going to watch. Actually, you can go ahead and answer G because I'll explain it here. So when a cost curve is flat, so that's basically like at this point with the long run average cost curve, when it's flat, then when we double the input costs or double the input, we're going to double the output. So that's called a constant return to size. When a cost curve is decreasing, so in this section here, when the cost curve is decreasing, that means that when we double the input or the total cost, our output more than doubles. So that's a good thing for a company. If they are getting out more than what they're putting in, that's increasing returns to size. So this is increasing return to size, and you can just label it on the long run curve. We don't have to do each individual one. And then the cost curve is increasing. So here the long run cost curve is increasing when if we double inputs, our production less than doubles. So we're putting in more than we're getting out. We're putting more money in than we are getting value product out. So this is decreasing returns to size. So decreasing returns to size is a bad thing. You're putting more in than you're getting out from a business standpoint. So you would not operate at that point. You would want to operate well, we need a little bit more information, but your lowest cost of operation would be at that lowest point at the constant returns to size. So go ahead and watch this YouTube video. The link is on your note sheet, and it's also on the slides, and answer all of these questions. I'll let you do that on your own, but it explains some of these concepts with some different examples. So go ahead and watch that video and answer A through H on your own. If we are given a price that companies can sell their product for, and we're given average cost curves, we can figure out how much money the companies are making. So let's go ahead and answer a couple of these questions. So which firm is the largest, producing the greatest quantity, and which firm is the smallest, producing the smallest quantity? Well, quantities are along the bottom here, and they increase as we go over to the right. So the firm producing the smallest is firm number 1, and the firm producing the largest quantity is firm number 4. So largest is number 4, and smallest is number 1. Say the price that we can sell the product for is $10, and say that businesses are producing at the point where price equals the marginal cost. How much money is each firm making and losing? Okay, so for this, the marginal cost for each of these firms is different. So we can see here that we have a marginal cost curve for firm number 1. We have a marginal cost curve for firm number 2, firm 3, and firm 4. So they are producing at the quantity where marginal cost equals the price, because that is going to be our profit maximizing point. So firm 1 is producing at a quantity of 25. Firm 2 is producing at a quantity of 50. Firm 3 is producing, so we have to actually extend this cost curve up, is producing at a quantity of 60. And firm 4 is producing at a quantity of 80. And all of their costs are different too. Okay, so we have to remember that total costs are average cost times the quantity that they're producing, and then profit equals revenue minus total cost. So the revenue, let's calculate the revenue of all of these first. So let's do, all right, so we have firm 1, let's just do firm 1 first. Okay, so firm 1 revenue. So revenue is going to be the quantity that they produce and sell times the price that they sell it for. So the quantity that firm 1 produces, again, is 25, and the price that they sell it for is 10. So that's $250 revenue for firm 1. What it is going to cost them to produce this, though, is we have firm 1's average cost curve right here. So we follow 25 up. Let's get a different color. We follow 25 up to the average cost curve. It meets the average cost curve right here. We follow that over. So that's going to be about, I would say it's close to 11. So it's going to cost them $11 per unit to produce. And again, they're making 25 units. So their total cost is going to be $11 times 25. And 11 times 25 is 261. So they're going to bring in $250, but it's going to cost them $261. So they're going to actually have a loss because profit is revenue minus total cost, so it's 250 minus 261. So they're going to have a loss of $11. So firm 1 is going to have a loss of $11. All right, let's write that down. Firm 1 has a loss of $11. And now we're looking at firm 2. So let's erase some of this. So firm 2, we need to first calculate their revenue. So they're going to be operating at a quantity of 50, and they're going to be able to sell their products for the same price, $10. So their revenue is going to be $500. What it's going to cost them, their total cost, the quantity that they are producing, 50, times their average cost at that point. So we're going to follow up 50 to the average cost curve. It meets it right there. Then we're going to follow that over. So that looks like that's about $7. We have 5 here, 10 here, so that's about $7. So 50 times 7 equals $350. So their total cost is $350. Their revenue is $500. So 500 minus $350. Their profit is going to be $150. Okay, so firm number 2, profit is $150. If we look at firm number 3, let's erase 2's information. Firm number 3 is going to operate again at a quantity of 60. They're going to sell theirs for $10 just like everyone else, so they're going to have a revenue of $600. Their average total cost is going to be where their average cost curve meets the quantity that they're producing, which is right here. And if we follow that over, that's going to be $5. So they're paying, they're producing 60 and it's costing them, so total cost equals 60 units times $5 per unit. That's all it's costing them to produce. So 60 times 5 is 300. So their revenue is 600 minus their cost is 300. So their profit, 600 minus 300 is $300. So $300 profit for firm 3. Firm 4, they're producing 80. Let's erase this. Firm 4 is producing 80. They're also getting that price of $10 when they sell it. So their revenue is $800 and their cost, total cost, is where the average cost curve, so this is their average cost curve, meets the quantity that they're producing. So if we follow that over, that's also on this $7 range. So they're producing 80 units times $7, so that's going to be $560. 800 minus 560, so revenue minus minus cost is going to give us their profit. So 800 minus 560 is going to be their profit is $240. So we'll write that down from $240 profit. So that's what we're being asked. How much money is each firm making and losing? Got a couple more questions on the next page. Which firm is making the most profit? Well, the one that was making $300, so that's firm 3 at $300 profit. So in order to increase profits, should firm 1 upsize, meaning should they make more, or should they downsize and make less? Well, if they make more, you see their average costs are going to drop. So they need to upsize and get closer to the production that firm 3 is making, because their average cost will drop and they'll actually make a profit. So they need to upsize to drop their average cost. In order to increase profits, should firm 4 upsize or downsize? Well, the average costs for firm 4 are higher than the average cost for firm 3, so they want to downsize closer to the production level that firm 3 is operating at. Couple more questions. When average cost is higher than the price that we're able to sell our product for, are we losing or making money? Well, that's what was happening with firm 1. Their average cost of production was greater than what they were able to sell their product for, so they were losing money. Their average cost was, we said, $11, and they were only able to sell it for $10, so they're going to lose money. If price drops to $5, which firms are making money, which firms are losing money, and which firms are breaking even? So we don't have to calculate this out to figure this out. All we have to do is look at the graph to figure this out. So if the price is now $5, any firm that has an average cost greater than $5 is going to be losing money. Does firm 1 have an average cost greater than $5? The answer is yes, because their cost is $11. So firm 1 is losing money. Does firm 2 have a greater average cost than $5? The answer is yes. They had an average cost of $7, so they are losing as well. Firm 3 had an average cost of $5, so they would be breaking even. If it cost them $5 to make the product and they're selling the product for $5, they'd be breaking even. And then firm 4 has an average cost of $7, which is greater than $5, so they're going to be losing as well. We're going to switch gears a little bit and talk about the production possibilities frontier. So earlier in the chapter, we had looked at different combinations of input. So we had capital and labor, and then we had curves that told us, specific combinations we could produce X amount of output. So the same, we could maybe produce 20 units of output on that curve, and this curve, maybe we could produce 10 units of output. So this is similar to that, but now we're going to look at the various combinations of output that we can produce given the same level of input. So this is a company, Sunspot, that produces canned fruits and canned vegetables. The canning process is similar for fruits and vegetables, and it takes about the same amount of labor and the same amount of equipment energy and the same amount of cans and so on and so forth. All of those inputs. So with all of those inputs, they could produce these various combinations of canned fruit or canned vegetables. So if they decided to produce all canned vegetables, they could produce 90 cans of vegetables and 0 cans of fruit for a given level of input. Or they could produce, if they chose to produce all canned fruit, they could produce, that looks like 138 cans of fruit and 0 cans of vegetables given a specific level of input. Or they could produce any point combination on this graph. So they could produce 80 cans of fruit and 60 cans of vegetables. Ultimately, we're going to want to figure out what combination is going to maximize their profit. So we'll take a look at that in future slides. Anything that lies above the production possibilities frontier is unattainable. It's not possible with the inputs that this company has available to them. Anything that lies below the production possibilities curve is an inefficient use of resources because the company is not maximizing all of the inputs that they have available to them, and they're producing less than they actually can. So they are going to want to produce somewhere on the production possibilities frontier. We can calculate the marginal rate of transformation, which is similar to the marginal rate of technical substitution that we calculated earlier in the chapter 2, to find out basically how many cans of fruit would we have to give up producing in order to produce 1 can of vegetables. and vice versa. How many cans of vegetables would we have to give up in order to produce 1 can of fruit? So to calculate the marginal rate of product transformation, the equation is just the change in canned fruit divided by the change in canned vegetables. So we've done these change equations a lot, but the change in canned fruit would just be, fruit production 2 minus fruit production 1 divided by vegetable production 2 minus vegetable production 1. So given these, we'll do a couple of these together. I'm going to grab my calculator. So for this first one, if we're trying to find the marginal rate of product transformation between points A and B, the change in fruit, so fruit at point 2, we have 128,000 minus 135,000 divided by vegetable 2, which is 10,000, and vegetable 1, which is 0. So 128,000 minus 135,000 is negative 7,000, and then 10,000 minus 0 is 10,000. So 7,000 divided by 10,000 is negative 0.7. So in this case, we would have to give up basically 7/10 of a can of fruit to be able to produce 1 can of vegetables. So that's negative 0.7. Okay, if we do one more, we could go from B to C. So we would have fruit 2, which would be 119,000, minus fruit 1, which is 128,000. Erase these two. And then we'd have vegetable 2, which is 20,000, minus vegetable 1, which is 10,000. So we have 119,000 minus 128,000, and that's going to be negative 9,000. Then 20,000 minus 10,000 is 10,000. So that's going to be 0.9. So at that point on the curve, we would be giving up 9/10 of a can of fruit to trade it for producing 1 more can of vegetables. Okay, and you can kind of calculate those down. And you can check your answers with this slide here. So here is one of the problems that you're assigned this week. So we are to calculate the marginal rate of product transformation between points A and B, and then between points C and D. It doesn't specify what these outputs are, but let's just say they are corn and beans. So output 1 is corn, output 2 is beans. So between points, we have basically change in output 1, change in output 1 divided by change in output 2. So we're going to have change in corn divided by change in beans. So we'll have corn 2 minus corn 1 divided by beans 2 minus beans 1. So corn 2, so we can label this point 1, point 2. This can be point 1 and point 2. So corn 2, in this case, is 37. Corn 1 is 40. Beans 2 is 16. Beans 1 is 12. 37 minus 40 is 3. Negative 3. 16 minus 12 is 4. 3 divided by 4 is 0.75. So negative 0.75 would be your answer for A. And I'll go ahead and let you calculate B. The next questions that we want to answer, so we're given all of the various combinations of outputs that we can create with a specific input, but we don't know which will maximize our profit. What we need to know is the price that both products could be sold for in order to figure out the profit maximizing combination, or at least the profit maximizing revenue. This will tell us how much revenue will be maximized. It doesn't necessarily tell us how much profit will be maximized because, we have to be able to sell all of those products, and, if we're making more or making less, we might be changing the demand. But it will give us the profit. It will give us the maximizing revenue. So let's look at that. So in order to figure out the maximum revenue, we need to know the price of the canned fruit and the price of the canned vegetables, and we'll multiply each of those times the cases of each that we can produce. So given these examples, so how much revenue will each of these combination points bring in if a canned fruit is worth $25 and a case of canned vegetables is worth $33.33? So basically, all of these points, like this point, 135,000 and 135,000 cases of canned fruit and 0 cases of canned vegetables equates to this point on the graph, right? Point B on the graph is represented by 128,000 and 10,000 fruit. So each of these points, this is point A, this is point B, this is point C, D, E, F, G, H, and so on, okay? Just so you can see the relationship between these two graphs. So all we're going to do is we're going to take $33.33 times our canned fruit number here. So let's look at this. So our price of canned fruit is $33.33. And then for point A, our cases of canned fruit is 135,000. Our price of canned vegetables is $25. And our cases of canned vegetables in that case is 0. So $33.33 times 135,000. Let me get my calculator. 3333 times 135. It's a lot. It is 4,499,550. Okay, so then for the next one, you would sub in $33.33 times 128,000, and then 25. You'd have to add that then to $25 times 10,000. So $25 times 10,000 is 25,000. So you'd add 25,000 to 128,000 times 3333. This is 4,266,240. So add that to 25,000. And it's approximately 4,291,240. So ultimately what we're trying to figure out here is the greatest amount of revenue. So you can calculate those out and figure out which point will maximize revenue. So which point on the production possibilities frontier will maximize revenue. So that's what you're looking to answer on your note sheet. Go ahead and check your revenue calculations with the numbers here, and we can see that point B has the highest revenue, okay? That means that somewhere close to this combination, 128 and 10,000, actually I should say somewhere between point B and C is going to be our revenue maximization. and our revenue maximization is actually going to occur where the absolute value of the price ratio of the two different products. So a price ratio is figured out by dividing one product price by the other product price. So in this case, 25 divided by 33.33 is 0.075. That's the ratio of price. So where that is equal to the marginal rate of product transformation is going to be the revenue maximizing point. So neither of these equal, so the ratio is 0.75. Neither of these are 0.75, but somewhere in between those 2 points is going to be the revenue maximizing combination. And then it also occurs where the ISO revenue line is tangent to the production possibilities frontier. We haven't talked about the ISO revenue line, but we're going to do that now. So the ISO revenue line is related to some of the things that we've also talked about earlier, but this is the all points on the ISO revenue line represent the same, so ISO means same amount of revenue. So all of these combinations of cases of fruit and cases of vegetable will bring in the same amount of revenue. The slope of the ISO revenue line is the same as the ratio that we were talking about, the price of vegetables divided by the price of fruit, which is that 0.75. So that's the same as that slope. Okay. So for this particular ISO revenue line, if we keep the prices the same, $33.33 per case of canned fruit and $25 per case of canned vegetables, we're being asked what is the total revenue of any combination of products on this ISO revenue line. So basically how we would do that is take the price of the canned fruit times the cases of canned fruit plus price of canned vegetables times the cases of canned vegetables. It's going to be easiest to do that, calculate that at these extreme points. So if we spent all of our inputs to produce only cases of vegetables, we could produce 40 cases of vegetables, and each case of canned vegetables we can sell for $25. So 40 times 25 is $1,000. So that's how much revenue we can bring in. We can check that too if we spent all of our inputs on producing cases of fruit. It looks like we could produce 30 cases of fruit at $33.33. 30 times 33. Yeah, that's going to give us $1,000 as well. And then you could check any of the combinations in there as well. So the value of this ISO revenue line is $1,000. If the ISO revenue line represents a company obtaining a revenue of $1 million, what are they selling cases of fruit and cases of vegetables for? So again, the cases of fruit here are in thousands, and the cases of vegetables are in thousands, which we didn't recognize before. But if they obtained a revenue of $1 million, and they did that by only producing and selling cases of vegetables, they could produce 40,000 cases of vegetables. So the price of vegetables that they can sell them for in that case, we would just take 1 million divided by 40,000, and that's going to be $25. Okay, so they're using the same numbers here. And then if we brought in $1 million of revenue by just producing fruit, we would be selling 30,000 cases of fruit. So 1 million divided by 30,000 cases of fruit is where we get that $33.33. Okay, so that we're charging per case of fruit. So these ISO revenue lines are similar to the budget lines that we have calculated in the past. The ISO revenue line, just like the budget line in the past, can shift. So it can shift to the right and it can shift to the left. And this is one of your practice problems too. So if prices of products remain the same, what accounts for a shift to the right? Basically if consumers purchased more, then revenue would increase. So, and a reason that consumers would purchase more is there would potentially be a change in income. Okay, for consumers, you could put change in income, or you could put consumers purchase more. They purchase double. Okay, and then, or consumers purchase less. So in this case, they're purchasing half the amount. So half, double, and again, that's due to consumers purchasing twice as much or half as much, or their income increasing twice as much or decreasing by half. The ISO revenue line can also not do a complete shift, but one of the points can change, and these would be a result if the original ISO revenue line is this and then it changes to this. We're changing the price of vegetables. So the price of vegetables, if now it takes us 200 cases of vegetables to make the same amount of revenue as it previously did 100, that means our price cut in half. So this is going to be a change in vegetable price. So it cut in half when it takes more to create the same revenue. And in this case, the price that we sold it for doubled. Okay, because again, revenue is staying the same, but now it only takes us 50,000 cases to produce 1 million, so the vegetable price that we can sell it for doubled. Okay, and I'll let you figure out what happens to the fruit prices in example D. So this just shows that you can put together the ISO revenue line with the production possibilities frontier and the point where it becomes tangent to the point where the ISO revenue line becomes tangent to the production possibilities frontier is the combination of each output that you would want to produce in order to maximize the revenue. Okay. All right, with that, good luck on the problems for this week and the quiz, and let me know if you have any questions.